Welcome to a lesson on Euler paths and Euler circuits. To begin, a walk is a sequence of vertices such that consecutive vertices in the sequence are adjacent in the graph. A walk in which no edge is repeated is called a trail, and a trail in which no vertex is repeated, except possibly the first and last, is called a path. An Euler path is a walk through a graph which uses every edge exactly once. An Euler circuit is a walk through a graph which starts and ends at the same vertex and uses every edge exactly once. This indicates an Euler circuit is an Euler path which starts and ends at the same vertex. Let's look at the graphs below and determine whether the graphs have an Euler path and/or an Euler circuit. So looking at the graph on the left, notice all the vertices have degree 2. We can start at any vertex. Let's go ahead and start at this top vertex. We'll label it S to indicate where we're starting. And now we determine if there's a walk through the graph which uses every edge exactly once. And we typically use arrows or numbers to show the direction of the walk. I'm going to go ahead and use arrows. Because each vertex has degree 2, once we start, there's no question in which direction to walk. Notice the walk is now complete, and we used every edge exactly once. This indicates the graph has an Euler path. We also started and ended at the same vertex. The graph also has an Euler circuit. Looking at the next graph, let's start the walk at the top vertex. And now we walk through the graph and see if we can use every edge exactly once. So we can go down. We need to decide whether to go left, right, or down. In this case, it doesn't matter. Whichever direction we go, we get stuck. We cannot continue the walk unless we repeat an edge, which is not allowed. This doesn't mean the graph doesn't have an Euler path or circuit. We can try starting from a different vertex. So let's try starting at the vertex in the middle. But we do run into the same problem. Whichever direction we go, we get stuck. The walk cannot continue unless we repeat an edge, which again is not allowed. The graph has no Euler path and no Euler circuit. Looking at the next graph, notice how 4 of the vertices have degree 2 and 2 of them have degree 3. Let's try starting at a vertex with an even degree, let's say here. And now we walk through the graph. Let's go right, right, down, left. If we go up, we're going to get stuck, so let's go left again. Then we have to go up, and we're stuck again. The walk cannot continue unless we repeat an edge, which again is not allowed. Again, that doesn't mean the graph doesn't have an Euler path or Euler circuit. We can try starting from a different vertex. So let's try starting with one of the vertices that have an odd degree. Let's say this middle vertex here. And let's start the walk. Let's go right, down, left, left, up, right, down, and now we end the walk. We were able to walk through the graph using every edge exactly once. The graph has an Euler path. However, we did not start and end at the same vertex. The graph does not have an Euler circuit. For the last graph, we should recognize this as the graph from the 7 bridges of Königsberg problem. Let's try starting at this top vertex. And now we walk through the graph. We go down, down. Let's go up, up, right. And now we need to decide whether to go left or down. Either way, we're going to get stuck again. If we go left, the walk cannot continue unless we repeat an edge, which again is not allowed. The same thing would happen if we went down instead of left. So you may want to try this a few more times, but this graph does not have an Euler path. It also doesn't have an Euler circuit. Before we go on, let's check the degrees of all the vertices in the graphs. There is a connection between the degrees of the vertices and whether a graph has an Euler path and/or an Euler circuit. Going back to the graph on the left, all the vertices have degree 2, or we can say all the vertices had an even degree, and the graph had both an Euler path and an Euler circuit. For the next graph, 4 of the vertices have degree 1, and one of them has degree 4. We have 4 vertices with an odd degree, one with an even degree, and the graph had no Euler path and no Euler circuit. For the next graph, 4 of the vertices have degree 2, and 2 of them have degree 3. We can say 4 of the vertices have an even degree, 2 of them have an odd degree, and the graph had an Euler path but no Euler circuit. And for the last graph, the degrees are 3, 3, 3, and 5. All the vertices have odd degrees, and the graph had no Euler path and no Euler circuit. So again, the goal here is to find a quick way to check whether a graph has an Euler path or an Euler circuit, even if the graph is quite large. And again, there is a connection between the degrees of the vertices and whether a graph has an Euler path and or an Euler circuit. A graph has an Euler path if and only if there are at most 2 vertices with odd degree. So if all the vertices have an even degree, or at most 2 vertices have an odd degree, then the graph will have an Euler path. A graph has an Euler circuit if and only if the degree of every vertex is even. Let's take a look at 4 more graphs and determine whether they have Euler paths and or Euler circuits, now by analyzing the degrees of the vertices. Starting with the graph on the left, let's find all the degrees of the vertices. We have degree 2, degree 4, degree 3, degree 3, degree 4, and degree 4. The graph has 4 vertices with even degree and 2 vertices with odd degree. Because the graph does satisfy the condition of having at most 2 vertices with odd degree, the graph has an Euler path, but no Euler circuit because all the degrees are not even. Looking at the next graph, we have degree 3, degree 3, degree 4, degree 3, and degree 3. One vertex has an even degree, 4 vertices have an odd degree. Because more than 2 vertices have an odd degree, the graph does not have an Euler path and also does not have an Euler circuit. Whenever a graph doesn't have an Euler path, it will never have an Euler circuit. And for the next graph, we have degree 2, degree 4, degree 4, degree 2, degree 4, degree 4, and degree 4. All 7 vertices have an even degree. This indicates the graph has both an Euler path and an Euler circuit. And then for the final graph, we have degree 3, degree 3, degree 3, and degree 5. All 4 vertices have an odd degree. We have more than 2 vertices with an odd degree. The graph does not have an Euler path and also does not have an Euler circuit. I hope you found this helpful.